Okay, so with no further ado, let's start this webinar. Just wanted to say hello, of course, and welcome to everyone today in this webinar. As some of you may know, because some of you have definitely been here in our past webinars, and thank you so much for that. My name is Tamara Ariel Mosqueda. I am from the Institute for Catastrophic Loss Reduction, and I will be hosting this summer session. So I understand it is summer and everyone definitely has vacation plans and we're all really very busy. So I really appreciate everyone who has decided to carve out time from their sunny summer days to join us for this webinar. And it's very interesting because we have a lot of really interesting presentations this month. Uh, sorry, just quickly.
Oh,
So we have really interesting presentations this month because we are joined with really amazing speakers and they will be sharing with us their work, their insights, and their recommendations. So if there's anyone else you think should be joining our session, so I will be pasting the registration link in a little bit more in chat box and also would be, and if you want to be part of our emailing list, please send us an email to pievc@iclr.org. So just quickly introducing our speakers. We have Cherine Akkari. She's a climate change specialist from Atkin Realis. We have David Lapp, who's a professional engineer, and he currently volunteers for the World Federation of Engineering Organizations, or WFEEO. And we have Nelson Lee, who's the president of Green Sky Sustainability Consulting Incorporated. So they will be showcasing how they have utilized PIEVC tools to assess climate risks and strengthen the resilience of infrastructure and assets in their own communities, organizations, and groups. Just a little bit of review of our agenda today. We have first assessing compound climate risks to northern infrastructure by Cherine Akkari. We have WFEO Model Code of Practice, which is introduction for engineers by David Lapp. And we have when climate likelihood approaches 100%, implications for long life infrastructure risk assessment by Nelson Lee. And then following the presentations, as usual, we will bring back all of our speakers for a live Q&A discussion. So we have the Q&A chat box there, so everyone can input all of the questions that they want to ask our speakers. So before we begin, just very quick housekeeping notes that this webinar is being recorded. It will be uploaded to the PIVC YouTube channel, and a link will be shared with all the attendees after the session. As I mentioned earlier, please feel free to use the Q&A box throughout the presentations and submit your questions, share comments with fellow attendees. Of course, we are always encouraging a collaborative and reflective discussion throughout the webinar because that's what makes it even more rich and interesting. And all of those questions will be addressed at the end during our dedicated Q&A session. So let's get started with our first presentation. So I'm ending my slides here so that Shireen can start sharing her screen. So really quickly, just a quick introduction to Shireen. So her first presentation is again climate risk and vulnerability assessment of the Environment Canada complex in Whitehorse, Yukon. So Shireen Akkari is a climate change specialist focused on climate risk and vulnerability assessments for infrastructure systems and municipal assets. So she has extensive experience applying the PIEVC protocol to evaluate climate hazards, integrating outputs from regional climate models, including downscaled CMIP6 projections commonly used in Canada to assess future risk reductions. She conducts a lot of risk assessments using PIEVC aligned methodologies consistent with ISO 14091 and ISO 31000 and integrates climate considerations into engineering design, asset management, and planning processes to enhance long-term resilience. She will be introducing to us a project that focuses on the federal complex, where Environment and Climate Change Canada monitors Yukon's rapidly shifting climate under siege by the forces it tracks. So using the PIEVC High-Level Screening Guide, or the HLSG, they screened 322 climate infrastructure interactions across 14 hazards and 3 planning horizons. They had also multi-day workshops with ECCC operators. And so the findings expose how compound hazards reshape risk at a pace that outstrips current design standards. And a concordance analysis confirmed the projected snow and wind loads will surpass current co-design and values before mid-century. So that is all really great, and she'll be elaborating on this project even further. Akkari, floor is yours.
Thank you, Tamara, for the introduction, and good afternoon, everyone. And thank you for joining today's PIVC webinar. So today, as Tamara stated, I will be presenting a CRiVA completed for the EC complex in the Whitehorse, Yukon in North Canada using the PIVC high-level screening guide. More generally describing the project provided an opportunity to examine how compound climate hazards are reshaping risk for critical federal infrastructures in the north of Canada and what that means in terms of adaptation planning over the coming decades. We see here on the screen the figure I put just to let you know that these two buildings are the two main buildings that constitute the EC complex, and these two buildings are the Combined Services Building and the Canadian Wildlife Service. So why this is important, or why this matters in this context? It's the EC complex is responsible for monitoring climate change across the Yukon territory and is itself increasingly exposed to different climate hazards. So the complex support, as you can see here, environmental monitoring, wildlife enforcement, and climate science through different programs. So as climate conditions change, protecting the infrastructure itself not only is important, but it's also important to maintain the service and the program the complex provides and support throughout the territory. So in this presentation, we'll see how climate risks are evolving, and many of those are compounded rather than being acted individual. So let's understand the site we assessed into more details. So as we can see, we see the two main buildings, which are the Combined Service Building and the Canadian Wildlife Services. And we also see 7 secondary buildings, which consist of garden sheds, flammable storage, propane tree shed, upper level warehouse, enforcement garage, another enforcement warehouse here, and an emergency generator building. The site is approximately 700 meters above sea level rise, and it sits in subarctic continental climate with sporadic discontinuous permafrost. Let's dig in a bit into the two main buildings that consist the site. So we have the Combined Service Building and the Canadian Wildlife Service on the right. So both have elevator units. One is older than the other one. In terms of roof, one consists of metal, the other is asphalt shingles, which make it combustible in terms of when wildfires happen in the region. In terms of superstructure, the CSB has metal as well, and the Combined Wildlife Service had wood frame. For the AC units, they use mostly R22 condensing units as well, some of which were upgraded in 2018. In terms of envelope conditions, the CSB has more wear, that means more repairs, and the Combined Wildlife Service has a newer envelope condition, which usually in generally performing better. In terms of water infiltration, the CSB is slightly more, it has more issues than the Combined Wildlife Service building. In terms of backup power plant, the CSB has a dedicated backup power building, as well as an internal EPDS battery pack, which is the emergency power distribution system. For the CWS, it does not have any associated backup power, but only has an internal EPDS battery pack inside the building itself. After having some, doing some research about the site and validating all the components with the stakeholder associated with the site, we came up with 4 components, infrastructure component categories, which are the two main buildings, as I said, was there, very detailed system building, roof system, exterior walls, etc., etc. So these are the subcategories. We also have the secondary buildings, which I also show in the picture in the previous site map. Site civil consists of access road, parking areas, and stormwater management system. In terms of operational activities on the site, we have loading and unloading activities. We also have emergency power distribution, system operation, and propane storage and flammable materials handling. So what makes this site-specific mostly vulnerable to different climate variables? So one of the key messages is that climate change in northern regions rarely arrives as a convergence. So for instance, below ground, we have the permafrost degradation, which affects mostly foundations, buried utilities, and drainage system. Below ground, we have intense precipitation. Here we're talking about mostly increasing precipitation, short duration, high intensity rainfall, rain on snow events, which place growing stress on roofs and site drainage. And on the other hand, we have the fire and lightning was really very common in the Yukon region. So with that, all these hazards interact with one another to create risks that are usually bigger than the sum of their parts. Let's dig in a bit into more details. For example, here we have what permafrost has emerged as a critical driver of landslide occurrence in Whitehorse. We see here a landslide hazard susceptibility map for the area, which identifies high to moderate risk, emphasizing permafrost monitoring areas and climate-driven vulnerability under future warming scenario. For sure, for now, the EC complex sits, as we can see here, whatever in the green square. We see it in like low to moderate risk rating for now, but with future climate variables accelerating, the risk category is going to shift. For instance, here we see also like a steep slope with intense rainfall, permafrost degradation also going to affect the upper level warehouse, which is wherever secondary building were close to the hill here. So also like with rock slide may damage the exterior shell and the foundation, which will require some major upgrades in the near future. So with that, how did we assess all the components, including the variables and vulnerabilities associated to the site? We applied, as I said, the PIEVC high-level screening framework. So the first step is we define the scope that includes the physical boundaries of the site, the associated components, and the climate hazards. Second, we gather the climate projections as well as facility condition information and operational knowledge. And for the building conditions, we also relied on site drawings that were given by the client as well. And in this case, we required our team to have different type of engineer that include site, civil engineer, structural engineer, and electrical engineers mostly. And for the operational context, we also did a pre-workshop with the different staff working on that facility in the Yukon. And the third step, we assess the risk using the likelihood and severity ratings. We used here a scaling of 5. And the fourth step is how we know is the reporting. That includes the risk classification matrix, including adaptation measures and gap analysis. So one important note to note here is that the assessment was carried on an operational phase. So it was we were evaluating risk to existing infrastructure that is currently in service rather than risk associated with design or new construction. So here's the scale of the assessment. So this was relatively, as you can see here, a larger screening exercise. We assessed 23 infrastructure components against 14 climate hazards under 3 time horizons, using mostly the SSP 5815 because it was the most conservative scenario. It also was required by our client. And we also identified more than 80 adaptation measures. So a major strength of the process was stakeholder engagement. So the facility staff participated in a pre-workshop session as well as in multi-day workshops. and brought decades of operational experience into the assessment. So that point alone was very essential and critical when assigning severity ratings and validating the practical implication of the different climate hazards that we identified on the site. In addition to that, the assessment was driven by climate projections, of course, that were developed specifically for the Whitehorse. So as you can see here, a dashboard that summarizes the key climate indicators. Of course, we did evaluate more than that, but like just in terms of summary, these are mostly one of the simple climate indicators. So the message here is not a single number. So the takeaway is every indicator points toward increased exposure. As we can see here, like, yeah, even if some of them are decreasing in the future, for example, the cold spell are increasing, but also they have a consequence on increasing, for example, rain on snow events. What else? The freeze-thaw cycle are decreasing, but also would affect the degradation of permafrost in the future as well. So with more warmer temperature, we can see increasing rainfall intensity, changing snow condition, longer wildfire season as well, and all contribute to a higher future risk under both scenarios, SSP 245 and SSP 58.5. So as we can see here is so what the challenge is when it comes to these climate variables, for example, is to understand how the trends interact with the infrastructure systems. So, and with that interaction is where compound risk becomes very important. So the slide here illustrates the idea of compound hazards. So for example, we have the permafrost thaw, which weakens the ground supporting infrastructures. At the same time, rain on snow events increase water volumes entering the drainage system. On the other hand, we also, or similarly, we have the longer wildfire season, which increase the exposure of different infrastructure component, while also raising the lightning frequency, which increases the ignition potentials. So these hazards are not additive; they amplify one another. So this is why the importance of the compound climate hazards come into as a key theme into this assessment. So what we are going to see in the next slide is 3 examples that emerge as some of the important compound risk for this facility. So by the late century, as we can see here, the active layer is projected to deepen substantially with ground temperature crossing the thaw threshold by mid-century. For this facility, this means, foundations, bird utilities, drainage systems, and access roads all become more vulnerable to settlement and ground movement. So the takeaway from this slide is many infrastructure systems depend on the stable ground, and that stability cannot be granted anymore. The second indicator that was important from this assessment was the rain on snow event. So we can see here that ROS events are projected to more than double by late century. So these events generate rapid snowmelt, increase roof and drainage loading, and create localized flooding and ice hazards, as we can see here. So what is particularly important that system designed to manage the water system may already be affected also by permafrost degradation at the same time. The third was the fire and mostly lightning, because most in the Yukon region, most wildfire are caused by lightning. So since most large Yukon wildfires are lightning ignited, so these trends reinforce one another, as we can see here. So vulnerabilities include electrical system. Some buildings didn't have any surge protection in place. Also, very important system was a propane storage in this particularly because no lightning protection, of course. The HVAC system of the building did also have not adequate smoke infiltration, which was a very important critical point as well. So yeah, we can see here how these vulnerabilities are becoming very important for the EC complex site. So what we can see here, so after evaluating these hazards individually and collectively, what we did overall, the risk profile looked like. So we can see here, so after screening 322 interactions, the overall picture is reassuring a bit, but also concerning at the same time. So most interactions remain low risk today. However, nearly 1/3 are already moderate risk to higher risk category, with permafrost and lightning responsible for many of the highest risk interactions. The current message is that climate risk is not a future issue for the facility. It's already happening on the site and having compound climate hazards already occurring on the site as well. So how risk compound over time? As we can see here, when we compare near-term and late-century conditions, risk clearly move upward. Major risk more than double, significant risk nearly double, and low risk interactions become much less common. So the takeaway here is climate change is not creating entirely new risks. It is amplifying existing vulnerabilities and pushing them into a higher risk category, as we can see here. And some of the interaction increase faster than others. So on the slide, we see the risk escalation. So the fastest growing risk across the entire assessment. As you can see here, several interactions involving propane storage, lightning, and permafrost reached the highest risk score by mid-century. And these interactions are very important because they combine high likelihood with high consequence. So we can see here that one of the key messages is, lightning is the dominant future risk multiplier, pushing multiple infrastructure system and operation system into the major risk category by mid to late century. In addition to that, we have permafrost degradation remain a critical risk driver, with several component hazard interaction reaching or maintaining minimum risk levels, approximately 25, which is the highest one. A roof system showed the broadest risk escalation with increasing risk from lightning, short duration, high intensity rainfall, long duration rainfall, and rain on snow events and snow accumulation as well. And we have landslide hazards and indicators associated to precipitation and rainfall are increasingly important drivers of infrastructure risk, and particularly for warehouse, drainage system, and site operations. So which hazards drive the most risk? So as we can see here, across all time horizons, two hazards consistently rank above the others. We have the permafrost and lightning, and we can see here driving the highest risk category scores. The lightning emerges as a critical threat to fuel storage, electrical system, backup power, and roof systems. As well, roof systems face the broadest range of climate stress, highlighting the need for immediate targeted adaptation measures as well. Here it's basically a precision, but we can see mostly lightning and permafrost are the most high indicators, very important indicators in this assessment. So the next question is, are current design standards sufficient to maintain whatever new changes we have in this facility? So we downloaded the ground snow load from the PCIEC Valley DVE design from Climate Data Canada. According to that, we did the projections, and we noticed that the snow loads are also approaching, the limit and exceeding the NBC 2020 design values by mid-century under SSP 5815. Driving rain pressure also is increasing. exceeding also the envelope design assumption. Wind loads are slightly increasing, but also, having consequences for the envelope penetration and cladding stress as well. Cooling days are increasing by like a lot increasing, and buildings are not usually currently designed for sustained warm season cooling. And we also saw in the previous slide, IDF curves are also increasing. So we noticed that the NBC, for example, or standard design do not account really for compound hazard interaction. They probably take them individually. So in terms of the adaptation measures, we assessed, well, we came up with more than 80 adaptation measures, as we can see here. So the goal is to integrate adaptation into normal asset management rather than treat it as a separate initiative. So that being said, as you can see here, many of the adaptation measures are low-cost actions that can begin immediately, such as inspection, monitoring, and improved maintenance. Others involve longer-term capital planning, investment, including equipment upgrade, roof improvement, and permafrost-related interventions. So with that being said, the assessment also has taught us many points here, as we can see. So the project, in fact, showed how the PIVC framework can translate climate scenario infrastructure decisions. It provided a structured approach to prioritize risk, support stakeholder engagement, and create a transparent basis for decision making. Perhaps most importantly, it provided a common language for discussing climate risk among different stakeholders that includes engineers, operators, and planners. So of course, no assessment is without limitations. So here are some of the limitations that came to us throughout this assessment. We have to keep in mind that compound hazards are not explicitly represented in the PIVC, especially within the scoring framework. Okay, so more specifically, there's no formal mechanism to capture multiplicative effects, example, permafrost weakening, etc. So risk scores may understate the true compound exposure. The second point was some data gaps remain, particularly for site-specific permafrost condition. More specifically, the severity calibration required significant professional judgment beyond what standard guidance provides. So this is why we had to do many pre-workshop with the staff at the federal site as well. One other data gap was that the screening level assessment designed to prioritize risk rather than replace detailed engineering. So this remains high level. One of the other major data gaps is that, unlike flooding, we had to rely on the landslide vulnerability assessment. So yeah, we relied on historical susceptibility map, but it doesn't exist, like there are no projection for landslide like flooding. So what we did for the projection is we had to rely on indirect, climate variables such as the ARI, the antecedent rainfall index, extreme precipitation, snowmelt, and rain on snow event projections. So what this assessment teaches us, so first we have compound hazards are becoming a defining feature for northern climate risk. The second point is that projected climate conditions are increasingly challenging existing design assumptions. The third point is that stakeholder knowledge is very essential for producing meaningful risk assessment. And finally, the PIVC framework provides a powerful starting point for identifying climate risk and supporting adaptation planning. So with that, I will conclude. And I thank you for your time and for your attention.
Thank you so much, Cherine. So that was really interesting. I actually have a couple of questions, but I will be saving that for a Q&A session. And speaking of Q&A session, if you have any questions for Cherine, make sure that you don't forget to input your questions in our Q&A box below. So, without further ado, I will be proceeding to our next presenters. We have David Lapp, and he will be sharing insights from the WFEO Model Code of Practice, Climate Adaptation and Resilience for Engineers, an introduction. So, a little bit about David. He is a professional engineer with 25 years of experience in climate change and engineering. His focus has been on climate risk assessment and climate adaptation or resilience strategies for public civil infrastructure and buildings at all three levels of government in Canada and in several countries internationally. Before I proceed, David, you can start sharing your slides. And while I finish, your really interesting detail about David's career is that he actually served as a project manager and program manager for the development and offering of the PIEVC Protocol as for climate infrastructure risk assessment on behalf of Engineers Canada between 2005 and 2020. So he'll be talking about something that he was very much involved in developing. And following his retirement at Engineers Canada, he served as a part-time consultant at the Institute for Catastrophic Loss Reduction as well, assisting the integration of the PIEVC protocol into their operations. So a little bit about the project that David would be talking about is that WFEO has recently published an international guideline on climate adaptation and resilience to inform all engineers worldwide of their professional and ethical obligation to consider our changing climate in their practice. Further, to document the results of their consideration, it lists 15 principles, providing further amplification and implementing actions for each one to guide engineers to adapt civil infrastructure and buildings to increase the resilience to climate impact and enable faster recovery. So, David, you can start your presentation. If you need any assistance with the sharing, please let me know.
Okay, so I just want to go through the code of practice and give a little bit of an engineering, I guess, lesson, shall we say, engineering 101 to start with. But before I do that, maybe people don't know that much about WFEO and what it is. So it is the global organization for the engineering profession, and it's been around for almost 60 years now. And it consists of over 100 members that are the national and international engineering institutions. And total number of engineers registered in these institutions is over 30 million. So we're a very large community and a very potential market, one might say, for the use of the PIEVC protocol. Engineers Canada is the member from Canada. And the main goal of the WFEO is to achieve the UN Sustainable Development Goals through engineering. And in the case of climate change, really it's the common denominator for the achievement of the UN Sustainable Development Goals, in that changes in the climate actually will impact the achievement of all of the SDGs. And if you, for example, if you have making progress on infrastructure, poverty, you can have a major climate event and wipe out all of that progress. So the idea is that if we address climate change, then we can make a substantial improvement towards achieving the UN SDGs. The WFEO consists of also has 15 standing technical committees and working groups, which include climate change. And then there's some of the other themes that are listed there below. I'm not going to go through those, but just to say we've got quite a few groups looking at different issues from a technology and engineering point of view. So I begin by just saying right up front, for all engineers that are on this presentation, and I'm giving this presentation to many audiences around the world. We've just started to do this rollout. The model code was published in June, so we're at the very early stages, but we're increasing awareness. And the first message is really that engineers have an ethical and professional responsibility to consider climate change in their practice. And this applies to all disciplines of engineering. There is no exceptions. in one way, either directly or indirectly, climate
David,
change will have an impact on practice to varying degrees, of
David,
course.
David.
But we all have to consider that, given that there's no question that the climate is changing. We have science behind it, 25 years of science. When I first started, of course, there's lots of skepticism about climate change, but the evidence now and in the future is irrefutable. And given that fact, it is up to engineers in their practice to look at climate change. Of course, there's two strategies, adaptation and mitigation.
Sorry, David.
Sorry.
Are you sharing are you using slides right now?
Yes, I am.
Sorry, your slides are not showing.
Oh, really? Oh, I'm sorry.
No worries.
Uh, okay. Try again. Share. Is this is it showing now?
It is not yet.
Oh, geez. Okay. We tried this morning, right? And it was working.
Yes. Give me a moment. I can also share your slides if needed.
My apologies to everyone.
Oh,
Is
great.
that thing
Cherine.
now?
Yes.
Okay.
Thank you.
All right. I'm just going to try and catch up here. Okay. So I've talked about WFEO. I've just gone through the notion of the ethical and professional responsibility to consider climate change. And now we'll talk an engineering one for a moment. So the idea here is that climate change adds an additional load to an infrastructure, and it can be a small change in climate. So it doesn't have to be like a huge thing, but it can be a small change. And just to go basic, you design an infrastructure with a certain capacity. You have a load, so the capacity obviously exceeds the load. You want to make sure so it doesn't fail. You add a safety factor. That's common for engineers to add a safety factor to account for things like uncertain ground conditions or properties of materials, that sort of thing. As the infrastructure ages, its capacity reduces, and then you have weathering on the infrastructure that maybe not been accounted for in the design. Meanwhile, on the load side, you have an increase in load because of the use over time. A good example is, say, a bridge across a river is designed for 10,000 vehicles a month, say, and now because of population growth is now 15,000. But because you have that safety factor, you're able to absorb that additional load. But then a severe climate event comes across and adds a load to it. So the load exceeds capacity and you have a potential failure condition, which is something engineers must avoid at all costs and prevent at all costs through their designs, their engineering practice. So given that as that scenario and how climate influences the interaction with the capacity loading on an infrastructure, I just want to go through a notion. How does this link to climate? So if you have a particular climate variable that has a mean and variance kind of, and you set an infrastructure threshold. So this is a climate design factor. You can see that to the right of that shaded area is where there's a potential for failure to occur. And obviously you can't make it invincible. You have to allow some ability to handle most of the events, but there is a small chance that threshold could be exceeded. So with climate change, you see say a shift in the say the mean to the right. So now you see that the area under that curve, which is the probability of exceeding that infrastructure threshold, is now greater. And the other, so you're seeing a variance, for example, as well. And you can see that the area in the curve gets even larger. So in that case, therefore, if you keep your infrastructure threshold the same as it was based on historical data, you're actually, as climate changes, you're increasing the chances of that threshold being exceeded. So what is the strategy for that? Well, you want to shift that threshold to the right to reduce the area under that curve. And that is where the notion of probability and consequence and risk assessment comes to bear, and was really the basis for why we developed the PIEVC protocol to do that. Because you're trying to reduce risk, can't make it zero, but you can certainly reduce it by, for example, shifting that threshold level to the right to I guess, handle more situations of higher climate variable. So here's a risk assessment matrix. This one typically has 7 levels, but of course, as was shown earlier, you can use 5 levels, 3 levels. So the protocol allows you to choose that. But the notion here, the strategy here for engineers is take a scenario where a flood has a low probability of occurrence, but has a high consequence. But because of climate change, the probability that area under that curve increases. So therefore, it shifts it into a high risk situation. And so the idea is to adapt climate adaptation measures to reduce that flood risk down to an acceptable level. Not necessarily zero, because that's very expensive to do, but down to a level that's acceptable, so that this exceeding those threshold values is reduced, chances of that happening, right? So that's where the whole notion of risk assessment comes to bear and how it impacts on engineering practices. In my view, it's a vital tool for engineers to understand what to do with respect to infrastructure and climate change, which of course, by extension to PIEVC being the tool that does that, makes the value of this, I think, very relevant and useful for engineering decision making. And as I mentioned at the beginning, we have 30 million engineers worldwide that we need to educate about this. And is being done through this model code of practice, which by extension goes into PIEVC and climate vulnerability and risk assessment. So how does a model code define climate resilient infrastructure that's planned, designed, constructed, and operated to withstand climate impacts and an ability to recover and restore service? So it's not just about the design, it's not just about the construction, it's not about entirely about the operation and maintenance. It also is how do you deal with the events. So that includes things like disaster risk and recovery, planning, and operations. So I always say to engineers should have a voice in those decisions, not only the design and construction phases, because it's to make this resilient, you need to be able to recover quickly. So, code of practice, mentioned at the beginning, we have 15 principles, and they're divided into 3 groups. And the goal of all this is that engineers consider the implications of climate change, and they create a clear record. So the idea here is that you're trying to demonstrate that you consider climate change and you document that. And if you do that, then you have met your professional obligations and discharged your professional liability. No one can say, oh, you didn't consider climate change, my infrastructure failed, and you are professionally liable for that. And the PIEVC tool is a beautiful tool to demonstrate the consideration and documentation of the climate, because you take that information forward into your engineering decision making. Now, there's 6 principles listed here under the ethical and professional side. First one being, of course, as the message at the beginning, adopt climate considerations into practice. There's several others listed here under the ethical and professional practice, and I'm not going to go through them here, other than to say, for example, number 5 is the precautionary principle. When you don't have complete certainty, then undertake precautionary measures. And PIEVC analysis is an example of a precautionary measure. Of course, nothing is complete in this kind of practice guide with some guidance on climate and climate consideration. So you want to know what climate information you need, both presently and for future projections. And the other important tool, of course, is existing codes and standards and guidelines. As we know, those are often delayed, or they're still, in some cases, historical, not necessarily accounting for climate, but they are to stand. There are a minimum, and engineers should consider exceeding the minimum to account for climate change. And then the last number are related to the practice itself. As mentioned in the PIEVC example previously, working with multidisciplinary and multi-stakeholder teams, you need the perspectives of the experts, the people that are going to be impacted, that sort of thing. So this takes a multidisciplinary and stakeholders approach. So it's not just engineers. You need to work with others, the operators, climate scientists, and so forth. Also important to consider the life cycle of the infrastructure. Are we looking at 25, 50, 100 years, which is the typical life cycle? And basically for clients that are owners of infrastructure, if you can't convince them to look at life cycle, you're going to have trouble against integrating climate change, because climate change occurs in that kind of time frames. So, but normally in asset management, we're talking about life cycle. I think that's getting better. Number 11, of course, is the one directly talking about PIEVC and the use of risk management, and the text includes reference to PIEVC. And of course, these other things are also things like nature-based solutions now. Those are coming into play for engineers. And then communication and language. And the last one's really important, I think, for all engineers, that this is a lifelong learning process. Keep track of the trends, what's going on, the tools, and so forth. Engage in lifelong learning to keep yourself up to date on the latest thing. So that's a very brief explanation of 15 principles. Just to show you in the guide itself, or the code itself, there's a summary document which has about 2 or 3 pages, lists the 15 principles and a brief explanation of what they mean. And then we have an interpretive guide. It's about 60 pages altogether with introductory sections and bibliography of pretty good bibliography of where to access information, and other guidelines in that, like the American Society of Civil Engineers. And so the structure is describing the principle, amplifying the principle, and then implementing action. So it's to be really practical. It speaks to an individual engineer. What do I need to do? What can I do? What are some examples? And of course, not all apply in all situations. It depends on the project, schedule, the costs, the inclination of the client. Are they risk averse or risk willing to take risk? That sort of thing. You need to establish some of those understandings to come up with the best solutions. And the role of PIEVC, I think, is an important piece for this presentation, to say that engineers need to consider the climate change and document. So the PIEVC tool does that and shows that. And so I would, in my opinion, it discharges this obligation and the professional liability behind that. It results guide and document the judgments that you need to take as an engineer to adapt to your infrastructure. And it also provides guidance where there's no legislation or regulation. There's many countries in the world that have very little legislation or regulation, so this is a reference. And of course, in dealing with this issue, there's a lot of competing interests. Obviously, the client, the society that the infrastructure serves, the project team, and so forth. And really, the bottom line is that the final results and decisions are often at the purview of the client. So your role as an engineer is to inform the client, give your best engineering judgment, And unless you're delegated the authority, you have to leave the decision up to them, unfortunately, in some cases. So the application, that's the scope of this. Just to give you a bit of a sense of it, is to inform and provide guidance. It's advisory, so we're not looking at a mandatory document. This is not a legal document, but it helps to guide judge, give you some ways to think about the issue. And it's yeah, so that's that. Then the adoption is that, as mentioned, WFO is not a legal authority. Model codes of practice are to provide guidance on specific areas and elements of professional practice. We have another in WFO called Sustainable Development and Environmental Stewardship, which is a code of practice. It's a sort of a companion document to this one. And we instruct WFO members to adopt the code of practice in whole or in part on a binding or non-binding basis. They can modify or edit to reflect local circumstances, the regulatory environment, status, of authority. And the other option, which happens in Canada, is that you have certain standards like the CSA standards may be integrated into contract, and those such cases, those become legal binding. So my just closing remarks here, I would say in conclusion that climate consideration is an essential component of engineering practice. All engineers should consider climate change, even if it, in this case, in a case of a project, it's not applicable, that they document that they considered it and consider it non-applicable, and that's documented. And it could happen. Also, the way to bridge, I guess, climate change is to use climate risk and vulnerability assessment and enable the translation of the situation scenarios into priorities, as you saw in the previous presentation. This is where we should spend our money or our resources first, second, third, whatever, to plan it out. And I would also venture to say that the demand for this by owners and clients and engineers is increasing worldwide. So I really feel that there's a super opportunity for PIEVC applications internationally. And this model code will help us do that. So that's part of my job, is to go out there and talk about this code and yes, promote PIEVC as the means to get people to actually know what to do about climate change. And lastly, I would just say, as an observation, is that climate services and data projections, even climate design standards, are available and they're improving. I think the last example shows a really good example of, if you were to try and do this 20 years ago, the data that you would have had would have been very sparse, difficult to get, and so forth. And I think you can see a lot of improvement there. It'll only get better, and that's all to the good for what we need to do. So, and here is the link to the model code practice. And so I encourage all of you to download that, have a read, see what you think, give me some feedback about it. We're always looking to see if we can improve. And of course, the messaging behind it, if there's anything you feel that be important to emphasize to other engineers worldwide or to non-engineers like the United Nations or other professions, that this is where engineers stand and this is where they're going to go with their practice, then please contact me with your thoughts. And I thank you very much.
Thank you so much, David. I hope everyone or a lot of people would contact you in order to give you the feedback that you needed for this, and it's definitely a really good presentation. Thank you so much. Proceeding to our next presenter, we have the final presentation from Nelson Lee, who will share his insights on his project when climate likelihood approaches 100%. So, Nelson, you can. Nelson, you
Thank
can.
you very much, Tamara. I think I need to get permission to share. But good news is I'll probably be fairly quick on mine. And it actually, the presentation from Cherine was very good as kind of a segue into it, because it's just another risk assessment that for my case studies, if you will.
You can just
Now
unshare.
you have to go. Oh, share. Yes. Okay. There you go.
There you go. Perfect. Okay,
Presentation is
so
there.
Nelson, you're preparing for this. Just quickly about Nelson, he is the founder of the Green Sky Sustainability Consulting Incorporated and the author of Smart Climate Moves, Strategies for Future Sustainability. So he is a seasoned professional with 4 to 5 years of global experience across various industrial sectors. He specializes in greenhouse gases quantification, verification, and climate change risk and resilience strategies. So this session specifically invites discussion on the implications of hazard likelihood approaching 100% within asset design lives using insights drawn from climate events to long-lived infrastructure assets in Canada. It draws on completed and ongoing climate change and resilience assessments applied during the design and operational stages of infrastructure with service lives up to and exceeding 50 years. So rather than presenting a single case study, this session poses a critical question for practitioners. How should risk assessment frameworks evolve when climate hazards are no longer uncertain but effectively inevitable within the lifespan of infrastructure? So we have to note that this assessment work is ongoing, and the session is intentionally structured as a practitioner-focused discussion rather than a prescriptive solution. So Nelson, you can start your presentation.
Okay, Tamara, looks like I got the wrong slides, but these will work. Wait a minute. Oh, sorry. Actually, as a matter of fact, I really did get the wrong slides. These are for what I did for engineers and geoscientists BC. That's the presentation. I apologize. Yeah, there you go. Yeah, and I will be fairly quick because I think you've got some good background from before. But as I said, it's a discussion
Sorry,
and,
Nelson.
and kind of, oh, you're not sharing?
Yeah, Nelson's slides. I think I'm still seeing David's slides. I'm not sure if it's mine or Cherine, are you able to see Nelson's slides?
No, I cannot see them. Now it's coming.
Okay.
Now I can see it.
Okay, thank you. Nelson?
Continue to share. I guess yes. Okay. Sorry about that. Apologies. Yeah. So a bit of a discussion, like when it's hard is the heart of it is when it's hard to forecast what the likelihood might be. And so we've done a number of these climate lens assessments for all these different kind of infrastructure projects, right? So usually company or organizations or even municipalities want funding, and the government, the federal government says, okay, then do a climate lens assessment, which is a lot like the high-level screening guide, the PIEVC, the same kind of approach. But the challenge, or at least for us, came when, what is the likelihood? What should we assign to that, right? So those are the kind of the projects. So, and just a few examples that we came across, and I think there would be a lot more. But how do you forecast a heat dome? Right? The likelihood of that. Sometimes even extreme flooding. We just worked for a client in Manitoba, and they are telling us about 2 or 3 recent big flooding events in the 2000s, right? A few years ago, and then they have one right now, a big flooding event. So yeah, it's hard to say when. Even wildfires, like BC, for example, we went through that worst fire season on record, and we thought, oh, what's next year gonna? Well, it wasn't that bad, well, relatively speaking. Then it went bad again, right? So yeah, how do you do the likelihood? And storms, I think, come into that. Temperature increases, some precipitation event increases. Those are a little bit easier to project. And so, and then, so a question is, in our risk assessment, we do likelihood times consequence. How do we pick that up? And when you have, if you remember, Sharine's study, the slides of the projections, like the climate hazard projections, they're all going up. And as time went on, they're all getting higher and higher, right? And so for long-lived infrastructure in particular, the opportunity, like short, like 10 years, okay, how many times could you have a bad event happen compared to 100 years? Again, it makes it more likely in my mind. So just taking the standard risk assessment approach here, what the question is like, what do you really assign for likelihood? And yeah, here's the climate lens assessment's giving us something like that. The high-level screening guide maybe is a little bit more advanced because it gives it the baseline in the middle and saying, well, okay, the higher would be, if we get over this. And I suppose if it's even over 100%, it still is in the five, right? That's as high as it goes. So that may be quite a bit more helpful. But again, you also don't want to maybe overrate the likelihood. And so again, how do you assign? Is it 3, 4, 5? And so we can do this discussion later. This is really, do you agree that it's difficult to establish these likelihood ratings, especially for these kind of extreme events? And do we need something more, say more than maybe PIEVC has right now, or is it just a special case, special consideration that people should be aware of, like what Cherine said about the compounding effects? We need to think about that. And if regardless if you think it's yes or no, but if you have any solutions to this, I'd like to know that. That's the key thing. I'd like to, how do you deal with it? So I have one recommendation. I noticed Cherine mentioned that she used ISO 14091. Well, it talks about screening level assessments. So that's a good way to start, and I think that's ideal for everyone. But they do talk about impact chains. So this is a definition from the ISO standard, analytical approach, some kind of methodology that enables the users to understand how how given hazards, so various climate change hazards, can generate direct and also the indirect ones. So it's like the compounding. It's not just what happens directly, but some of these indirect things, and then propagate through a system. So if you're looking for a solution, maybe read about the ISO 14091 standard. It's just $200. And Canada has just released the Z version, CSA Z 14091. So some contacts. So I think that's all I wanted to say just for mine. If there's some discussion, and so I'll stop there. And looking forward to the Q&A for David and Cherine and myself.
I'm going to kick off the conversation a little bit and start with a couple of things I am personally interested in your presentation. Okay, so I'm gonna start with Nelson, and because it's really still really fresh. I want to ask what inspired the beginning of the study. So how did you decide you're going to investigate and you're going to future-proof risk assessment frameworks? And what has been the challenges so far when it comes to asking this question to many of our practitioners?
Yeah, I think the main one was, we've done a lot of wastewater treatment plants. They typically have a 20-year design life. They may operate for a lot longer, 50 years. But we did a few like pipelines and things like that, that maybe have 80, 100 years. Drainage, adaptation system, a drainage system, yeah, 80, 100 years. And if you start thinking, and this is where maybe my thinking could be corrected or whatever. What's the likelihood of it happening sometime in a 100-year period? Starts getting very, very high. And does it just become a consequence assessment? Like it's all 100, it's all, high likelihood, and it's just the consequences. That's where it's coming from. And what I've seen, just my anecdotal evidence is, boy, you get some pretty bizarre weather events. You're not expecting them, and suddenly, oh, this year we have a flood. No one was really talking about that. Or this year we have the wildfires, right? Or the big storms. And so, yeah, that's what so I'm wondering, yeah, am I right in assigning say a 4 or 4.5 or likelihood, or should it be a 5 or maybe even a 5 plus? I don't know. So that's a kind of a question. That's why I put it as a discussion. I know there's a lot of people who have wrestled with probably something similar, maybe have a solution for me.
Yeah, I'm actually urging any of our attendees, if they have also tried to do something similar or also ask the same question and what has been their experiences regarding that, please feel free to share your experience in the chat box. Thank you, Nelson. Cherine, I was hoping for a presentation if you can share or like tell us a little bit more about this the stakeholder engagement that you had. So what was challenging about it? What was interesting? What are the lessons that you learned that you definitely apply from the onset on your next projects utilizing PIVC?
So yeah, this is a good question, Tamara. So in terms of challenge, we had to rely first on, materials given by the client, of course. So we had facility condition assessment reports, and we had site drawings. So we had to, include different types of engineers to read the site drawings, etc. In terms of technical complexity. So also, in addition to that, the facility condition assessment, we also noticed that, you know, we had a chat with the staff, and we noticed some of them are not really up to date. So we had to do some pre-workshop meeting to rely also on the operational knowledge of the staff. So I can give you an example. For example, so some of the facility condition notes may maybe indicate there's no significant drainage deficiency on the site. But when we talked to one of the operational staff, he said, no, we have some flooding in the parking lot, recurring freeze-thaw related events. So this is how we were able to know that. So that was a gap that was also resolved by, talking to different stakeholders on the site as well. One of the challenges we had in previous project was, how we involve the different kind of multidisciplinary engineer in our project. So for this, we started early. We introduced early the project to them. So this way they have time to read all the materials that we're giving to them as well.
I see. And when during the beginning, was adopting the any PIVC material like a no-brainer, like a non-negotiable sort of decision from the start? Or was there a conversation that needed to take place and people to convince in order to ensure that climate risk assessment is definitely done for this project?
So this one was already given by the client, so we had to comply to what the client. So already the client knows what the PIVC high-level screening guide is. So we had to comply to our different RFP requirements. One thing is for the engineer is also we had to explain to them what is the PIVC high-level screening guide is. So we did a risk matrix. We went simply from one Excel sheet to another. Just make it simple. But some of them really understood the process very fast.
Mm, amazing. Yeah, it's a little bit it's not very complex and I understand from many practitioners who did comment on the PIVC that it is very much for general use. So it's
Mhm.
understandable. It's very easy to understand. Yeah, thank you, Cherine. So, for David, a couple of questions. So, I just wanted to ask, did you have any challenge when it comes, that you encountered when it comes to having engineers adopt the climate risk assessment principles? And what has been the most effective way that you have so far when it comes to dealing with those challenges?
Yeah, I think it comes down to training. So when I was developing the PIEVC protocol, we had a lot of training workshops, and we would have call these workshops across the country in all the provinces and territories. We would ask engineers to come. We'd organize them through the local engineering regulator, and we would have a day-long workshop where we would have, a case study that we'd start with, and go through the process, get people working together around tables. And one of the really nice things we did, I think, which was really helpful, was we would bring in a couple of users, people that had used the protocol, the clients. So we bring down a municipality or federal government, and we ask them to, explain how did they use the protocol, why, what problems they had. I didn't censor anything they said, and that was, I think, it was peer-to-peer communication, right? To help them. It wasn't just me trying to sell them something. It was like, here's somebody who's used it, and here are the good things and the not so good things and the challenges you might face. So I think education for engineers is really important. And just to go back to the model code, that is our intention, is to do some training webinars to dive deeper into the principles for, again, offering it to individual engineers across Canada and internationally. So,
And what are your future plans for the code? How are you thinking of encouraging more? So yes, you have the webinars, you have the discussions. Is there anything more specific that you have in terms of strategy for this?
yeah, we're going to work with the national members, so they represent their engineers in the country. It's very difficult to get to the individual engineer in, say, Nigeria. We'll work with the Nigerian Engineering Association. In Canada, it will be with Engineers Canada and all the 12 regulators in the different provinces who have the direct contact with their engineers. So my hope is to offer these webinars. I have kind of an introductory webinar which lasts about an hour, so goes into more detail. I'm offering that to all the regulators across Canada and to other countries, and then their encouragement will look to develop more, I guess, individual training sessions for principles that people need to understand better, or like, how do I work this into my practice, that sort of thing. So that's a future direction. And of course, it's funding and volunteers to help will be needed. So if anyone's interested to participate in anything like that, please send a message and we'll have a chat.
Thank you so much. I do want to give Shireen and David a chance to answer Nelson's question, just in case they do have anything that they want to add. I think it's very interesting. So, ask the question, how should risk assessment frameworks evolve when climate hazards are no longer uncertain and they're going to be inevitable? So, Shireen and David, do you think, in your own experience, how do you think you would answer this question when it comes to future proofing this framework?
So, in my experience and related to previous projects I did, we had to. I suggested to modify a bit the risk likelihood scoring according to what we get in terms of projections. So that was one suggestions. I know also other people use the seven scale likelihood scoring as well instead of the five. So that's also another suggestion as well.
Yeah, my comment would be is one of the things we need to establish with the clients is their risk tolerance. So, and that's not an easy thing to articulate in a way. So, when you're looking at a 100-year timeline and we have climate change, so historically maybe that event would have happened once. Now it's going to happen 5 times, say, during that 100-year period. Is the client willing to, I guess, accept that? For example, if the one event was to seriously damage or destroy their infrastructure, are they willing to do that, 5 more times over the 100 years? And I think that's the answer is obviously yes. But so then that leads the conversation. What do you do about that? How do you do that? So that's a piece, I think. But also in the likelihood, I take the comment around the shall we say the linked, or what do we call them? Trying to think of when you have consequential impacts. So one thing happens that leads to another. We need to be able to handle that because that's an additional level of understanding. So, maybe if you prevent the first thing from happening, then the second won't. But it's to understand, and link those events together. And the methodology for that requires a deeper level of investigation, and probably means more time and cost because it takes more time to work that out. Probably a workshops would be required. So it would be extending the process and deepening it, probably through multiple workshops. But that again costs time and money, and how far will the client be willing to do that? If it's a very very expensive facility, say, I, I like to say wastewater treatment plant versus an individual building, maybe it's worth it for the capital cost. But these are factors that have to be weighed, into how much level of detail you can go in to explore those things.
I
Amazing.
found that very helpful, especially on the risk tolerance of the client. That's ultimately that's where we're driving to, right? And not so much of figuring out what the climate is. Yeah. One thing I didn't say, and I should have, is our climate science is getting much better, of course, but it's predicting what the climate, or forecasting, I guess, projecting what the climate will be in the future, not the weather, right? And the weather could be, it seems to me, anything, and it's the weather that gets you, right? At least if it's like a heavy rainstorm or something like that. Or yeah. Anyway, thank you very much. Appreciate that input.
Yeah, I hope all of that helped you, Nelson. So those are really interesting answers. I do want to add something. I understand that a lot of the let's say preparations that we do is can be based on business as usual scenarios, can be based on like forecasts on compounding risks. I think it would be great to explore or make it a little bit more standard to explore disruptions, what disruptive scenarios that may not always be part of the business as usual, can be a little bit out there, all your white swan black swan sort of like cards, and see how we actually deal or engage with those disruptive scenarios. So I think that I have talked to a couple of practitioners that do usually deal with just forecasted data, and that's and how do you call this? Like a little bit more linear in nature, and so something that's a little bit more out there when it comes to experiences for extreme weather events are usually scenarios that I find really interesting when it comes to discussions. Yeah.
One thing that we want to do is engage with the emergency response folks a lot more. Like bring some of those folks into the workshops so that they can bring their perspectives to, what are we going to do if this happens and what are the consequences? They would have had experiences in the past with, dealing with extreme events and the responding to them. And that an additional value put into establishing consequences.
Agreed. Conferences that I have attended with emergency response managers, their experiences have been really interesting, very grounded, very practical, and yeah, it would be great to always have them on the table because they also talk about the very social experiences of it and like how they engage with the people who are affected, the people who are on the ground and stuff. So yeah. Thank you so much. I do want to read one comment from Derek Gray in our Q&A box. He thanks all of our speakers and he says that it is very interesting with significant increase in likelihood scores. My experience to date with clients is that this is very much a learning process for them. Of late, we are providing and highlighting the future climate projections in addition to the likelihood scores. A lot of the work that we have done is for specific assets, not all of the assets that a client may be responsible for.
Mm.
Yeah.
Yeah, I certainly agree with that. Yeah, very helpful. Oh, one thing I'd like to plug for, I know we just a little bit more time. I did mention the impact change in 14,091. So, I mean, the standard is only $200 or something like that. Canada just published it. Lots of really good references of Canadian work, provincial work too. So for $200, you get all those references, and then you can read about impact change, which is slightly maybe an alternative a little bit to PIEVC. Different approach, but it's looking at maybe that consequential bit too, David.
I was also suggest that we look at the procurement side of this business because that to me is a weakness. Often that's not climate risk and vulnerability assessment is not called for or specified very vaguely, and it makes it difficult for consultants to respond. So I think some work and focus on that area to make procurement practices more standardized and inclusive of this would be a real big step forward.
Yeah.
Do you have anything else that you want to add, Shani, before we end our session?
Yeah, just want to add some note, like in a previous project, Tamara, as you were discussing the different scenarios, we took in a different project, the SSP 370, for example. And we took the SSP 5815 for the bounding analysis to compare how the risks are, evolving across different scenarios. But we also found, like, sometimes IDF, for example, we cannot, get, projection for example, for the SSPC, 70 as well. But, some data gaps remain in terms of that specific scenario, and like, more method, like more accurate methods need to be provided in order to, focus on that scenario more than the SSP 5815, for example.
Can I clarify, like, was there a study or assessment of like how scenarios can possibly evolve?
Not in that specific, but like, the client requested to, follow the SSP series 70, for example. But, for the IDF, we were able to calculate projection for that specific scenario using a specific formula given by Environment and Climate Change Canada. But it also required some, specific detailed calculation for that. So it was a bit more complicated.
Got it.
I would also just say one more thing about using climate information. There is still a judgment call with the use of that information. If you're, again, understanding the needs of your client, the number may say this, but you may say, you know what, I think we should maybe increase that by 10%, even though that's what the number supports, because to cover off those unforeseen events, for example, right? And so there's still an element of engineering judgment that's needed in the use of climate data.
Yeah,
Agreed.
that makes sense. Also, I noticed one thing, if you use a higher scenario, like, as Cherine was suggesting, it looks bigger, to the average person. And remember, a lot of people in our workshops are more lay people as far as climate change goes. They may know their infrastructure very well in engineering, but so if you say, oh, there'll be maybe a 10% increase in, rainfall events, it kind of almost falls on deaf ears, right? You say, oh, it's doubling or something. Oh, wow, now it wakes them up. So I think it just, maybe that's a human nature thing, in my experience. So we use the extreme one, right? Worst case scenario, even though it may not happen.
I want to read Alice Dixon's comment. In my experience, likelihood scores are derived from calculations of change trends in weather parameters, while the consequence scoring is the element that depends on human risk tolerance. So that is
Okay. Is that in the chat by chance or somewhere
Q&A.
in the Q&A? Okay, I don't see oh, there it is.
Yeah.
Okay, good.
Amazing. So yeah, I think that these are really great comments. And if there can be further discussion that can be derived from this, please feel free to email our speakers. I'm sure that they would appreciate a lovely discussion around this. I would like to slowly close our webinar. We have 3 minutes left, but because it was a very great discussion. Oh, sorry. Sorry. I want to ask one more question by Alice. Any advice on how to convince an engineer that usually 10% load buffer is not sufficient when the climate change trends are less than 10%? No worries.
David, you probably thought about this a lot more.
Yeah, I think you have to be conservative, like engineers are conservative, and that would be a recommendation. Again, don't necessarily make the final decision. We should probably do as much as we can to document why we think that. But it is, and again, a judgment call, and it's up to the client to say, do I accept that or not? And then if they don't, then I guess you have a discussion about, well, if it's not that, what should it be? And that's when it gets really interesting.
I can reply to that a bit from my experience. I also find it kind of helpful to focus on the threshold instead, rather than percentages. So
Yeah.
even the projected climate change is less than the traditional design margin, for example, it might still significantly increase the frequency of threshold exceedance, right? So small changes in climate condition can also translate into much larger changes in risk. So
Yeah, David's graph.
That beginning slide, I would encourage everyone to use that slide. I've been using it for over 20 years to try to explain how climate impacts on engineering loads and so forth. And it's quite an effective way of showing people that aren't engineers necessarily, but they can see what the implications are. And that way, it's a bit of education that gives a better context for why you're recommending these things.
And also, this is more the prepping, but building a case based on other case studies as well that might be using more than 10%, and it worked perfectly, worked perfectly fine for that project, or it was very beneficial for all the stakeholders involved.
Yeah.
So that's the data that could sort of support that action. Thank you so much for this rich discussion. It was great. Everyone had really great insights. I would like to thank our speakers again for joining us for this July session, for sharing everything that you know, your experiences regarding your own projects. So we do want to keep this discussion going. We have two more sessions for September and for December. December will be the final session of the year. And as usual, I would send details out for anyone who might be interested in becoming a speaker, whether it's an ongoing or a finished project. We would love to hear from you. Just message pievc@iclr.org, and we will be reviewing your emails. And of course, this is going to be a great opportunity for anyone who would going to be a speaker to disseminate and show your work to help others learn from your experience. So, oh no, there's one more question. Yeah, but I'm going to send this question. There's one more question, but I'm pretty sure that if you email our speakers, they would enjoy answering your question. So sorry. But yeah, thank you so much, everyone. And thank you for being a part of our July session. We are excited to see you again in the September session. Thank you.